Should I start? I want to say a few words. I have said that earlier, but I want to emphasize that, elaborate on it. The idea of the rational thermodynamics is we question everything. We are so used to using Gibbs equation and all these thermodynamic relationships, Navier-Stokes equation, but the idea is to question all of them. Not that they are not correct, but they have been developed, as I said earlier, often either for simple system, now equilibrium thermodynamics, or empirically, which is fine. I mean, they are based on centuries of experience and a lot of observations. They have been developed by great people. But the question is, we want to know, are they really coming from one single fundamental and one single approach? And that's the idea. For example, if you take a Gibbs equation, we didn't assume it. We didn't assume anything related to it. In fact, we assumed a very general dependence of A, if you remember, the free energy, on the velocities. For porous media, we said it depends on velocity differences. We started with that. We started with depending on temperature gradient. We can put in rate of dependence, rate of change of temperature. We can put that all in there. And it is the second law that tells us, no, those are not allowed. That's the only dependence you will have. And then if you take this, then you can see, okay, look, I take the derivative of this. This is dA d rho, d rho, plus dA d omega, plus dA d theta. Then I say, what is dA d rho? Yeah, those who know thermodynamics, they say, okay, that's related to pressure. But why pressure? Which pressure? Is that the one that I put a tensiometer in the soil and I measure, or a transducer in the water I measure? Is that pressure, the dA d rho? Who says that? Where is that coming from? How about when it is flowing, I measure it? Is it the same or not? And I say, oh, that's a good question. How do I measure pressure? Now, one of the things is that I put a tensiometer or a transducer at a given point, and if there is no flow, I measure it, I get a value. If there is flow and the pressure hasn't changed, I make up my setup such that at that point, the pressure doesn't change. Then I say, oh, okay, so that is a state of stress under those conditions. And what is a state of stress? No, I have this, I got this relationship. That the state of stress, this is a derived relationship. I have here PF, but it was actually dA d rho, if you remember. When I went through maybe I can go back to the entropy inequality. Oh, sorry, it's not here. When I had entropy inequality, I had this term. And even if there is flow, I determine that under equilibrium conditions, this is equal to that, must be equal to that. And that's the state of stress. So, and that's what the transducer measures. It's measuring forces. It's not measuring dA d rho. That the pressure is dA d rho was a derived result. And I think that is the strength of this approach. And once again, thankfully, for the rational thermodynamics, we get the results we already have. We know. For example, I showed you Gibbs equation, you can get it. But how about, once again, it's a more complex system. How do we know that it's the same? If I have two-phase flow, how do I know that the pressure of a phase is not the dV of that, the du dV of that phase? Maybe other phases should affect it. It's a, as you said yesterday, it's a mixed system. At the scale of my observations and the scale of my modeling, I don't have just water and oil. I have oil and water everywhere. The transducer sees oil as well because it's measuring over many pores. Some of them filled with the... So that's the one of the major strengths of this approach, that we really can derive. And can you see that this Gibbs equation comes out of this? Because the AD rho I derived already. I showed you just a minute ago that this is equal to P over rho squared. I don't know what this is. It didn't used to be like this. There's something wrong with my pen. So this is rho squared, the rho, and that is the relative chemical potential of the component, the omega, and that was minus S d theta, and there is a 1 over rho squared. I can put that under here. I get d of 1 over rho, right? Because this is rho squared. d of 1 over rho is d of a specific volume, v over mass. And with a minus sign, by the way. So this is minus P dV plus mu the omega minus S d theta. There you go. And I did not assume it. It's not a starting point. It's a derived result. And every other point here, look, you can always assume dAdV to be pressure. Define it. Yeah, what's wrong with that? The AdV is pressure. As I said, is that the pressure I measure? Is it the same pressure that's in my momentum equation, momentum balance equation? And that's the, those are answered here. Yes, it was a derived result that dA d theta is minus S. It was not an assumption or a definition. Okay, so I thought it would be good to, because now I'm going to look at multi-phase flow, and there I obtain results that are not in the first place what I expect. And then I can say, oh, but something wrong there. I say, no, look, I did it for single phase. I got it. It is correct. It's what I always know from centuries of work. So what I get for multi-phase flow, and my result, I don't see why I should discard it, because it's not what I expected. And I show. Okay. So yesterday I derived these balance laws for a multi-phase. Where am I now? Yeah, maybe I'll start where I was yesterday. Can I possibly get some water? I have dry mouth. Is that a cup or something? There is water here. I only need a cup, actually. Yeah, so remember I derived these kind of equations yesterday from molecular approach, and yeah, these are the full set of equations mass balance, momentum balance. Wonderful. Thank you very much. I appreciate it. Remember, even the conservation laws are not as a starting point. They were derived from the molecular picture. The molecular picture was the starting point. And then we wrote this entropy inequality. There are restrictions, although all the exchange terms. And the second law is that the sum of all entropy production terms for phases and for interphases must be bigger than 0. And I have expressions for all of those. And I also assume further that the flux of entropy is related to the flux of heat for both phases and interphases. The external supply of entropy is related to external supply of energy. I define these Helmholtz free energy functions. And when I do that, the second law now has these terms in there. The first row is basically what we had for a single phase, except that very last term for the exchange of heat between phases and boundaries, which are interfaces. Otherwise, you have had that for a single, say, when I looked at only single fluid. Now it's written for 3 phases. It's a very similar expression for the interface. Again, this has a lot more exchange terms because it exchanges momentum with the phases. Note that that exchange of momentum multiplies the difference in the motion, in the velocity of phase and its interface. There is exchange of heat with the interfaces. There are 2 phases on the 2 sides of interface. So that's why we have the terms twice for the alpha phase and beta phase side of it. And there are terms related to the exchange of mass between phase alpha and interface alpha beta. And that multiplies the differences in free energies of the 2 and potentially a difference in kinetic energies. And that is for the other phase on the other side. And there is an exchange of heat with other interfaces through the common line. That's this term. Now, then we introduce the constitutive theory. By the way, if we count the unknowns, so let me show this is constitutive theory says that the causes are these: motion of solid, motion of fluids, densities of fluid. Actually, density of solid must be here too, because density of solid is not given anymore by its own motion because of porosity. So they are not related. But yeah, here, sorry, I didn't include rho s because there is porosity here. I could remove porosity and have rho s. Saturation, the mass densities for interfaces, there are 3 here. Interfacial area of interfaces, temperatures of interfaces, temperature of phases, motion of interfaces, and depends on the location of position. And then it says that all those fluxes and densities in the balance laws are functions of these. And are functions of these at all past times and all points of the space, of all those parameters. You know that for every unknown in the balance laws, a quantity that, you see, the balance are a limited number of equations. You have one mass for each phase, one momentum for each phase, and one energy for each phase. Those are the equations. There are unknowns like the stresses, but we give a constitutive equation for it. That takes care of that. Or if you have energy, there is a constitutive equation for it. If there is heat flux, now, all the terms, so let me go back to the one of the balance laws. For example, here, all the terms in here, there is a constitutive equation for it. So actually the energy equation is an equation for temperature. That is after you put in all the constitutive equations, formulas, once you derive them, you substitute the energy equation is formulated in terms of temperature. So temperature is the primary variable and you have an equation for it. Momentum is actually an equation for the velocity, because once you put everything back in here, then the velocity, you put in here stress tensor for in case of viscous fluids is pressure and gradient of viscosity, but pressure is given to us by state equation, is a function of rho and theta, so that's not an unknown. Gravity is given, those I have equation for it, so it's all in terms of velocity at the end. There is one problem when you go to both single phase flow and two phase flow. We have a new variable, that's porosity. We don't have an equation for it.
Mass balance equation of the solid?
You can use the equation of the solid for porosity if the solid real density is constant. Correct. So that's the only way out. And we have always assumed, okay, the solid grains are incompressible. Then you can cross out in the solid mass balance, you can cross out the porosity and the density of the solid. There you go. And then you get an equation for porosity. But if rho s is not constant, but you say, yeah, okay, for all cases, solid grains are incompressible. That's fine. The problem is saturation. For saturation, I don't have an equation. I am short of for saturation. And for interfacial areas, for the areas, area per volume, I also am short of equations. I don't have them. So for an interface here, unless you assume that the mass of interface per area is constant, then I have an equation. But if it is not, okay, then this is an equation for the mass density. I need an equation for interfacial area. And the way we resolve this is when writing these axioms and these constitutive relationships. So let me go through that. We did the following. So you go through this objectivity, admissibility, and so forth and so forth. That means, as you know, reduces gets rid of the Fs is a spatial position that cannot be, dependence on T is not allowed. The velocities, only the relative velocities are allowed. And you get a few of these, and now these are my set of dependent variables and a set of independent variables. And that set is simply all the unknowns in the, but I have added rate of change of epsilon as a constitutive equation. So that's how I account for my missing equation and a rate of change of saturation and rate of change of interfacial areas. Those are additional constitutive equations. Now I have enough equations.
I mean, you just prescribe epsilon dot then.
I say epsilon dot is a function of all of these. And S dot is a function of all of these.
Yeah, so but that doesn't help.
Why not?
Well, I could say that the temperature of the surface is a function of all of, well, it is a function of the temperature of the surface, but the time rate of change of it, yeah, is then a function of all these variables. I mean, that is of course true, yes. So, but what does it help?
Look, every it's an equation. So I count, if I count my equations, I have my balance laws. Mm-hmm. If you count them, we had 5 in case of single phase. We go to porous media, we have 15 for the phases, and I believe we have also 15 for the 3 interfaces. So I have 30 equations. But I have a larger number of unknowns. That includes those as well as the initial list of motion, velocities, and densities, and so forth. So I know if I count them, I have enough number of unknowns, enough number of equations. It helps.
So you say, for instance, epsilon dot is 0.
No, epsilon dot is a function of all of these 4.
Well, 0 is a function of all of that. I mean,
Yeah, but it's a very
is
specific
0.
value.
I mean, no, but that would be very convenient because then the porosity doesn't change, right?
Of course, yeah. If you have a...
For any systems, the porosity actually doesn't change.
That's correct.
Yeah.
Then, okay, then we do not include porosity as an unknown, and therefore we don't need an equation for it.
Oh, yeah, you just give it by epsilon dot being 0, yeah.
But how about if I have a system where the porosity is not the constant?
That is the important question, yes.
And then it's a function of all of these.
Yeah, but
These are causes. These causes will effectuate the change of porosity.
I mean, you say, okay, I have the following independent variables, and that implies that everything further depends on those independent variables. That is perfectly correct. I mean, however, if you don't have the equation, I mean, that doesn't tell you anything.
But I get the equation. Soon you will see I get restrictions on these S dot and epsilon dot from the entropy inequality. So I say it's an unknown arbitrary function of all of these. I say the same, by the way, about all the other ones.
Sure, yeah.
And then the entropy inequality give me restriction. If it doesn't, then you're right. Then it's useless equation to start.
Sorry.
Then it is useless. That's correct.
I'll ask a related question. I mean, because the description you use is you say it is coarse grained. You don't look at the microscopics. You look at the medium as a whole.
That's
but then,
correct.
if you, for instance, look at the generation of interface, I mean, take an example of microfluidics. The precise geometry of a channel determines whether things break up into droplets or not.
Yeah.
How is that in those equations?
No, why should it be? Is it
Well,
in,
I mean, you
is
say
it in any macro scale equation?
Well, I mean, you have something that says the rate of change of the interface, and that should be a function or a functional of all these other things, but I don't see how that kind of microscopic geometry ends up in these
It
concepts.
doesn't, because we are talking about the rule of large numbers.
Yeah.
We have an REV, defined for an REV, which contains a large number of pores of different shapes, large number of interfaces, and the idea is that this average quantity is not dependent on the details that happens in every single pore. That's the assumption. Otherwise, any macro scale is the same. You can ask about Navier-Stokes equation and the movement of molecules. The molecules hit each other, they may go this way, they may go that way.
I'm not talking about true microscopics. I really talk about something that is already coarse grained, but if I have a medium that consists of a large number, a macroscopic number of funnel-like shaped pores that open into something, and compared to cylindrical pores, then the interface generation might be different in the case of
Okay, then you will have different coefficients in your equations.
Okay.
Permeability will be different. Indeed, take the simple case of a single phase flow, not two-phase flow. In this case of single phase flow, the flow through a porous medium is a function of how the pores are shaped, what their connectivity is. Do they have a lots of tiny pores, big pores? All of that doesn't enter your macro scale. It only enters through some macro scale property. So porosity, permeability. Now, if there are cases, then you need more information. This doesn't work.
Okay.
Then you need to identify some other state variable that accounts for that. That is absolutely true. And that's why one of the arguments that it came out by itself that interfacial area between the two phases and, well, actually the three interfacial areas must enter the equations, because exactly what you said, volume saturation is a volumetric measure. Is that enough to tell us what is happening in a two-phase flow? I say it's not. Then we say, okay, let's look for another state variable, macro scale still, that gives you more information, and that is interfacial area, that tells you a given saturation, how is that distributed? Is it one big ball with a given area, or is it distributed? And then, so that's exactly right. I mean, there are always cases that you want to carry information from microscale to macro scale. What information do you want to carry? So we substitute these. Then we do something extra here. If you recall, for single phase flow through porous medium, we started saying that free energy depends on all those variables. Rho, temperature, but gradient of temperature, velocity of fluid with respect to the solid. You can put in gradient of velocity, and it becomes really messy. You get long number of equations, because if you do that, you have to dA dt, you have to determine the dA dt, and then not only for one phase, you have three phases, three interfaces, all the dA dt's in terms of these. No, it's not possible to do. Moreover, we have seen from our previous experiences with these operations, with these manipulations, algebraic manipulations, that the dependence on gradients and the velocities disappears. It's not allowed by second law. So at least in order to make it manageable and my own life easier, I have a restricted dependency. All the other functions, the stress tensor, heat vector, everything else here is a function of all of these parameters, but interfacial energies, I start with a restricted set of dependencies. Here again holds that you start with this, you get results that you don't like, you go back, you have to revise this. But this is in order to make it practically manageable to go through the entropy inequality. Then we say a phase free energy only depends on its own properties. Actually, later on we expanded it, we included dependence on interfacial area of the two interfacial areas surrounding the phase. For solid phase depends only on its own properties, plus saturation, because we really know that the solid properties, macro scale, you see deformation, depends on saturation. And for the interfaces, they depend on their own mass density and temperature and their own area, but also saturation. So that's a limited dependency. Yeah, one of the axioms I didn't mention that explicitly is called axiom of equipresence, which means that once you choose a set of independent variables, that is this set, all of them depend on this. Don't make a discrimination. That's the axiom of equipresence. But these are axioms, they are not theories. We propose them. We together subscribe to them. So we can also together decide, yeah, that's not a bad idea.
The energy of your interface does not depend on its curvature.
There is no curvature because I'm looking macro scale. Curvature is a micro scale property. It only exists, as you said, within the course. I'm providing, I don't see them. I don't see any curvature when I make observation.
If I have a cylinder, the curvature is everywhere the same. So for the whole surface, I have one curvature.
That is correct. Yeah.
You could consider a macro scale property just as much as in the surface area.
No, the surface area is a total something divided by total something for the whole REV. In very specific cases, that is correct. Curvature is given, but it's not a specific case. So in general, curvature is a microscopic property, same as pore size. It's not a macro scale property.
I mean, if I divide the surface area by the volume of the pore,
Excellent.
I get the curvature.
I have it here. This is curvature, if you wish. This is my macro scale representation of that micro scale property. I fully agree with you. That's exactly what A alpha beta is. And in fact, I can show that.
Can I ask one? I mean, it's just a question about semantics, but normally when you talk about axioms, those are things that can neither be proven or disproven.
That's correct.
But here you have an axiom where you say, and if it doesn't work, I have to add something.
So it cannot be proven and unproven. That's
Well, I mean, if it
that's
doesn't
what
work,
axiom is.
it basically, I mean, so if you can say, with these parameters alone, I cannot describe the phenomena that I want to describe, then that means that your axiom is incomplete, doesn't it?
It could be incomplete. That is
That's
correct.
okay. So that's the kind of semantics about axioms.
No, that's.
So I guess
that
that's
was
a
my
slight-
understanding
Okay,
too.
yeah, okay.
That the axioms are not laws, and you cannot prove them. You cannot disprove them. For example, axiom of objectivity.
No,
We
sure.
agree together that the behavior of a material must be independent of observer. That we agree together.
No, but it's a bit like with Euclidean geometry, that you say you have the axioms of Euclidean geometry, and you say, but in some cases you need something else as well. You don't.
Okay.
And so that's
Yeah.
why, I mean,
Yeah,
okay.
right. And that's why here I say, okay, I select one of my axioms and I'm happy with this limited set of dependencies for interfacial, for the free energy. So if I now substitute in the, remember, I'm sorry, I just go back and forth because I think it's really important to do that. So if you remember the entropy inequality, I'm not going to say those constitutive equations must satisfy this, which means that I have to replace the ADTs using the chain rule of differentiation. All the other dependent variables, they simply here remain, but actually you need to replace them with a functional of all those long list of variables. That's what we really have to do. Okay, now if you do that, even with this limited set of dependencies, I get a long, I get 4 pages of the equations or the inequality. But again, you should identify most of them, at least. See, that is the one you also got, the AD theta plus, sorry, that is S. At some point, when we went to two-phase flow, we had to change the notation because S we also use for saturation. So S we were using for entropy, we changed it to eta. Now, there were things like that. Gamma was the rate of production of entropy. We changed it lambda because we use gamma for the mass of the interfaces and so forth. But these are all familiar terms. You have seen it the last couple of days. Now, here is the stress tensor. I already have put the symbol P, but it's not that it was there. What was there was this. I had this there, and I have now already chosen to show this with the symbol P. Whether this is pressure or not, that comes out to say, okay, what is the stress tensor under for this material, and if it comes out to be that, then oh, this is pressure. But at this moment, it's just it. And you see the same for the, what is also interesting comes out is that there is a term here relating to the change of free energy of solid with density of solid. It's a kind of pressure. And it's not in the Terzaghi formulation, this is related to fluid pressure. But here, it's not necessarily directly related. We'll see whether it will relate or not. We have also here an interesting term, which is there actually, up there, that the solid pressure I just defined is in a combination with the pressure of water, wetting phase and the non-wetting phase. But it multiplies the rate of change of porosity. Then I have here exchange of momentum between phase and interface relates to pressure times the gradient of saturation, but there also a change of free energy with saturation. What else I have? I have also defined here, use the symbol gamma, but that is, it wasn't gamma originally there. What happened? I had it. Oh, okay, yeah, it's here. So it wasn't gamma originally, it was minus A gamma dA, the energy with the, this is alpha beta, you see? So, I'm sorry.
Maybe surface tension.
No, that's
Yeah.
the big house.
This is beta.
Absorption.
Okay, so I gave this symbol a name, but actually it comes in combination with here. It comes in combination with the stress tensor for the surface. So the surface stress state of stress is related to this term, which I identified as gamma, and gamma is interfacial tension. I think these are all terms related to the rate of change, rate of exchange of something. For example, this is rate of exchange of mass between a phase and interface, and it multiplies the difference in the Gibbs free energies of the two, and the difference in the velocities or kinetic energy.
Can I ask one thing about
Sure.
the surface tension? Because if you look at a solid-liquid surface interface, solid-liquid interface, then you have the surface free energy density, at least to use the thermodynamic terms.
Yes,
and
we
you
have
the
that
surface
here.
stress, and they're not equal. For the liquid, of course, liquid-liquid interfaces, they're the same. So, I mean, where would such a difference show up here?
I'm sorry, I missed the part you said. What is not the same?
The surface stress
Yeah.
and the surface free energy density.
Okay, so this is the, yeah, I understand your question. Let's see, where am I? Yeah, here. This is the surface stress, and this is summed over all three interfaces, so indeed it has solid and liquid interface or fluid interface included here. It is coming in combination with the surface energy as a function of per mass, basically. Because you can also show that this is the same as change of energy per area. This is energy per area, this is mass per area. So, and this is mass per area, you can reformulate this and show that this is the same as free energy per area. So it's exactly what you said, but it is there. I don't get anything different. If you really have a situation that's different, then we have to go back and see what is it we have to add in order not to get that here there is no distinction between a fluid-fluid interface and a fluid-solid interface. Is there anything you would like to share? I'm sure these discussions are also useful for others.
No, I was just trying to understand.
Oh, okay.
What was his question and what
Oh,
was your
okay.
answer? And I understand that you have a term there,
Uh-huh.
S a alpha beta minus gamma alpha beta I,
Uh-huh.
and that is not zero.
That is at this stage not zero yet.
Yes, the tension is not the same as the pressure, or the tension that the air is not the same as the energy density.
Well, it is not zero, but in a minute I will have to argue that it is zero.
Okay.
Okay, but at this stage they just appear together. So this is indeed a tensor. I'm sorry, this is.
So that's basically a pressure, and the other term is basically.
Well, it's not pressure. It's a state of stress within the surface. So it's tension. Actually, it's tension, and the interfacial tension. And this is the change of surface energy with mass or with area. And they come together, and I'm now going to argue that this is the deformation rate tensor for the alpha-beta interface.
Can I just say one thing about the...
Sure.
You say, what you write down is actually the variation of the surface free energy with mass. And then you say, or with surface area. For a liquid, that indeed is equivalent. But for a solid, there are two ways you can change the surface area. One is by stretching it, and the other is by adding mass. And for a liquid, basically, if you stretch it, mass flows into the surface, and then it is the equivalent. For a solid, it's not, and that's the point. So I think that this expression probably gives you indeed the surface free energy density, but it's not. It doesn't give you the surface stress. So that makes.
Okay. The reason I said that, I think at some point I had the derivation that this becomes. Really, yeah, maybe you're right. Maybe that's something else I had. That was surface tension. But also a solid, when you stretch it, its mass per density changes. Take a balloon. You stretch it, it becomes thinner.
Yes.
So mass per area changes.
No, I mean that precisely is the point. I mean, so when you stretch a solid, more things happen in the bulk, but then in the surface, things also happen as a function of the degree of stretching, and they're different. You can say they're slaved to the bulk density, so this is all fine. Like you can say you change the lattice constant in the crystal, but it is not the same as adding new material to a solid surface.
A surface you can, fluid surface you can extend it, keeping its mass density constant.
Absolutely, yes.
Yeah, I must say, in the framework of this operations, that's what I get. That's what I get, and if we don't have to do something about it, we have to go back then.
It's
Okay.
okay.
What I also, as I said, get here, I don't know what this gamma is doing here. I was adding things last night and then. I get that the exchange of mass between the phases and the neighboring interfaces is related to the Gibbs free energy, and Gibbs free energy for an interface is defined in this fashion, which is the standard definition. Okay. So here are some results. And the results are coming from the fact, if you recall, that a lot of the terms you are seeing there, they are multiplying. They are multiplying variables that appear linearly in the entropy inequality, and therefore their coefficient must be identically zero. One of the things that is here, you see, this is a function of all the parameters. Therefore, it's not appearing linearly because it's a function of, now here you have to have density and area and saturation, everything is in here. So this doesn't have to be zero identically. But this has to be zero identically. And there are few, and those few will give you this kind of results, that the stress tensor for in a fluid, the state of stress is isotropic and is related to the rate of change of free energy with specific volume, or if in extensive terms in terms of volume. Okay, and then for the solid phase, it has a part coming from its deformation, is a part related to the rate of change of its free energy with the mass of it, or its specific volume, and so that's effective stress. But what this is not given yet. And for interfaces, I get all three interfaces that the state of stress is just the interfacial tension. What is interesting is that there is in the, I have to go back, in the, is it here really?
This is.
Yeah, in the 4-page equation I showed you, there is also this term. No, here, this term. There was this, and I must say, this is not the way it was in the entropy inequality. It's always rate of change of energy, rate of change of atmospheric energy with density of the non-wedding phase. So I have replaced them with these symbols, but originally it was all those energy changes. And what this PC here, this symbol is this. So this was in my entropy inequality. And I identified this whole thing, I denote it by the symbol PC. I'm not saying it's capillary pressure. It's coincidence that is PC. But I denote this by PC, and what is it? Is the change of free energy of the system. We see all the free energies are here as a result of change in saturation. You change the free energy, if you change the saturation of the system, you will change its free energy. And the stronger this will be, the larger that PC will be. And the other way around. So these are related to each other. To me, we'll see in a minute, under equilibrium conditions, I find that Pn minus Pw is equal to this. And they say, oh, so that is capillary pressure, and this is the macro scale definition of capillary pressure. And yes?
When you talked the other day, I mean, how is time coming in here now? Because when you change saturation at different rates.
Yeah, so that is when you have non-equilibrium. Under equilibrium conditions, Pn minus Pw is equal to this. So the definition of PC is independent of Pn minus Pw. PC, the same way that pressure is identified as the state of stress under equilibrium condition, and we found it to be dA0. The same we find that under equilibrium condition, I'll show it in a minute, this animal is equal to Pn minus Pw. And they say, oh, that's what we measure as PC. Because PC didn't exist until people starting to measure it. So that's what do we measure? You put we have done that, hydrophilic transducer, hydrophobic transducer, we never measure PC actually. We always measure pressure of the fluids. And the difference is defined as PC. And that's, now I find that PC is equal to this. Okay? And in fact, if you say I neglect the change of free energy of phases with the saturation as the only important term, this can be reformulated to be surface tension times curvature. This is actually curvature, macro scale curvature, which accounts for all the areas and all saturations. If I can prove it that for a sphere, this is exactly curvature.
The curvature is proportional to 1 over the length. Why is that dA, ds proportional?
Because this is area per volume.
Oh, per volume. Okay, yeah, sure.
Yes. Okay. Now, this is what remains of the entropy inequality, is still 2 pages. Because it has all these non-equilibrium parts. I'll show in a minute, I define equilibrium to be when all the rates are 0, or the velocity differences are 0, or the velocity differences and rate of saturation, they are all 0, then under equilibrium, pressure of the solid is equal to, the thetas are equal, the pressure of solid is equal to the weighted sum of the two fluid pressures. And that's a known result in geomechanics. I find an expression for the exchange of forces between phases and interfaces. It gives related to that. And then I find that under equilibrium conditions, PC is equal to Pn minus Pw. I must say, this is 1989. We were doing this derivation, and I came to this result. PC is not always equal to Pn minus Pw. And I say, yeah, but I didn't know any better than PC is Pn minus Pw. So I have to get rid of this. And I went back to the equations. There was no way that I could prove or obtain as a result for all conditions PC is Pn minus Pw. It's only equilibrium. Non-equilibrium, this difference is proportional to its flux, or the other way around.
And in non-equilibrium, temperature differences therefore drive the saturation.
It could also indeed be because of that. There could be also
So you have an extra driving force.
Exactly.
But I didn't hear exactly what you said. In equilibrium, the rates are 0. But does it then necessarily imply that the bracket parenthesis
Yes, because
is
if you
also
recall,
0?
my argument, I went through this argument that if this is 0, this is 0.
Yes,
so at the
that's
equilibrium,
clear.
all
That's
terms
equilibrium.
0, then entropy production is at absolute minimum. Therefore, the rate of production of entropy with respect to the parameters, variables that make it 0, must be also 0. So if I take d gamma, the epsilon dot appears here linearly. D gamma, the epsilon dot must be 0 at equilibrium, gives me that these two must be equal. These two must be equal.
Yeah, that is it's a last statement I wonder about, because if epsilon dot is 0, the parentheses can be anything.
Not under equilibrium conditions. It's a look.
The entropy is a minimum.
It's a absolute
Okay,
minimum.
yeah, sorry. Yeah, now I remember.
So it must be that.
Yeah.
I suggest we take a break. And then